very happy to, I'm very happy to extend a warm welcome on behalf of Basic Science Department MCKVIE to you all. It is really a great pleasure that we have our participants from different parts of the country, including 24 states. We have an inhomogeneous combinations of teachers, students, and research scholars as participants, who all are assembled here with a keen interest to quantum computing. But before we switch over to today's session, let me take this opportunity to introduce our college to all of you. This is our college. After reaching Howrah station, a bus or auto is enough to take you to the college. It has been more than 2 decades ago MCKVIE started its journey. In this long journey, MCKVIE acquired a couple of feathers in its cap, like accreditation from NBA and NAC. Here is a list of the BTech courses undergoing in MCKVIE. That much. Our students are our pride, who are placed across the globe to serve for a better world. With this, I would like to request our principal sir to address to the participants.
Thank you, madam. Am I audible?
Yes, sir.
Thank you, madam. Good morning to all my colleagues and dear participants. I hope all of you are taking extreme safety measures to keep yourself and your family members safe from this devastating COVID-19 outbreak. Let me give a heartiest congratulations to the Department of Basic Science of MCKV Institute of Engineering for arranging such a workshop in such a large scale. The credit especially goes for the reason that this workshop has been arranged when we are going through severe restrictions in our states as a safety measure against COVID-19. I think the workshop will be of great help to all the participants in gaining knowledge about the latest concepts of quantum computing that will be discussed here. I would request all the participants coming from all parts across the country to utilize the scope in the best possible way. With this, I welcome all of you to this workshop and I wish all success for this workshop. God bless you all. Thank you. Thank you once again.
Thank you, sir, for your valuable words. Let us move on to today's topic. Quantum computing could change the way the world uses energy. Every time you use your phone, computer, or your smart TV to access the internet, you are sending data requests to warehouse sized buildings around the world, full of hundreds of thousands of servers, which are among the most energy intensive systems on the planet, representing approximately 10% of global electricity generation. Yet, we are still blindly making classical computers, which are only increasing the extraordinary level of energy consumption. This is just one reason why quantum computing is a key to the future. In addition to holding the potential to solve some of the world's most computationally challenged problems, quantum computers use significantly less energy, which could lead to lower cost and decreased fossil fuel dependency as adoption grows. Unlike classical computers, which use binary bits to encode information as ones or zeros, quantum computers work using qubits, which can represent both ones and zeros at the same time, allowing quantum computers to find optimal solution that classical systems cannot, all while using less energy. That much information, introduction, you can say, these were for our student learners. And with these few words, I would like to request Dr. Tanmoy Roy Choudhury to reveal the fascinating journey from classical to quantum computation. Dr. Roy Choudhury, Assistant Professor of Physics at MCKV, completed his graduation and master's both in physics from Delhi University and PhD from Indian School of Mines, Dhanbad. With a 12 years teaching experience, highly popular among students, Dr. Roy Choudhury is a keen learner most of the time who is engrossed with the fascinating world of theoretical physics, which includes quantum field theory and general theory of relativity. No more from this side. I request Dr. Tanmoy Roy Choudhury to take the charge.
Thank you, Debanjali ma'am. Am I audible?
Perfectly.
So, a very good morning to my colleagues and to the participants who are present over here. This talk, as you all know, is about will be a journey from classical computers to quantum computers. The basic intention or motive behind this webinar is to make you all familiar with the principles of quantum computing and how is quantum computing different than classical computing. And I understand that this webinar is attended by people with diverse backgrounds. So I have tried my level best to keep the mathematics as simple as possible. But as you can understand, the mathematics, a bit of mathematics is always unavoidable. So I will be dealing with a bit of mathematics. And I request you all to keep a pen and paper with you so that whenever required, it is my suggestion, whenever required, you can work it on your own, because it is always better to work things on your own on pen and paper so that you can understand. And see, please understand, quantum computing is a whole paper. It's about, it's a whole subject and it's a lifetime affair. So 2.5 hours or 3 hours at the most for this webinar will not be sufficient enough. So there will be many things which I'll skip. So this webinar is just to motivate you towards quantum computing. I'm not going to teach you quantum computing. I'm going to motivate you towards quantum computing so that interested participants can pursue their career in quantum computing. So I hope this, by the end of this webinar, you all will be interested in this emerging technology, the quantum computing, and you can pursue your career as engineers. See, people from diverse backgrounds are coming forward and contributing towards this branch of technology. Physicists, mathematicians, computer scientists, and whatnot. So people from diverse backgrounds are coming and they're contributing. I am from physics background, so I'll be focusing mainly on the physical principles on which quantum computers work. I'll be very basic with my definitions. I'll work out some of the mathematics which are required, and I'll definitely point out the areas on which you need to work out when you will study this quantum computing in detail, if you do so. So with this, I start my presentation. I hope by the end of this, you'll be motivated to pursue quantum computing. So is my screen visible?
Yes, sir, it is.
So the title that I have chosen is from bits to qubits. So you can understand, I'll take you through a journey from classical computers to quantum computers. And I'm Dr. Tanmoy Choudhury. I'm an assistant professor in the Department of Basic Science, MCKV Institute of Engineering. So let us start. What will be the flowchart of my presentation? I'll start with the motivation. Motivation is basically, I'll try to address the issue, why quantum computing? Why in the first place are we looking towards this new branch of technology? Why quantum computing? We have very good classical computers, so why go towards quantum computing? So we'll start with that. The motivation behind studying or pursuing quantum computing. And then I'll straight away move on to quantum gates. So we'll study a few quantum gates with what is the concept of a qubit in quantum computing, and then some quantum gates. And then I'll discuss probably the first quantum algorithm, the Deutsch algorithm, if I'm pronouncing it correctly. The Deutsch algorithm, this is probably the first quantum algorithm. And this algorithm, if you understand it correctly, this will explain, or this is sufficient enough to explain the computation power of a quantum computer as compared to a classical computer. And then we'll do some hands-on using IBM Quantum Composer. So maybe in between, I'll switch over between my PPT and IBM Quantum Composer to show you the hands-on, or to have an hands-on experience. So let's move on. The motivation. At first, what I'm trying to question is, why do we see some processes happen in one direction and not in the other? Say, for example, there is a shape, let's say a harmonic oscillator, or let's say this is a shape of a bowl, and you put a marble on the bowl, and that marble will slide down to the bottom. You drop a pebble on the pond, and you see ripples spread out, and you drop an egg, it splatters. These are processes happening in one direction. Do you see processes happening in the reverse direction? The question might seem inappropriate in the given context, but I'll try to make a connection with quantum computing. So let us first answer this question. Why do we see some processes happen in one direction and not in the other? And we all are aware of that answer. The answer is, it is highly unlikely for the entropy, which is denoted by S, of an isolated system to decrease. And we all know, this is the second law of thermodynamics, that entropy of an isolated system always increases, or it remains the same. It never decreases. So that is the entropy. So in every case, the process that we see, in those processes, the entropy of the universe, which is an isolated system, always increases. So why does the reverse process not happen? Because the entropy would decrease. But that does not answer the question, why don't we see some processes? I think we should go deeper into it. But first, let us ask the question, what is entropy? And it was Boltzmann who proposed this concept of entropy. And we all know this entropy is given, the S is given by the Boltzmann constant into the logarithm of omega, which is given over here. And what is this omega? This omega is basically the number of ways, the different number of ways in which a configuration can be achieved. Say, for example, you have gas atoms or molecules of a gas in a room with a given temperature and pressure. These temperature and pressure are the macroscopic properties of the system. Now, if you swap two atoms or two molecules, if you interchange them, see, it's a different combination, but the macroscopic properties has not changed. So the temperature and pressure will remain the same even if you swap atoms. If you have different combinations of atoms that are being swapped with each other, the entire macroscopic properties are going to remain the same. Right? So these are different combinations or different ways in which you can achieve the same configuration of the system. The more the number of ways you can do it, the higher is the entropy. That is written over here. If omega is larger, that is, if you can do things in a larger or a greater number of ways, then the entropy will be larger. There is another word for entropy to understand entropy. Entropy is the degree of measure of randomness. So the more random the system is, the higher is the entropy. Now the question is, how do you quantify randomness? The randomness can be quantified by this equation, and that is omega. So if you can do things in more number of ways, that is, if omega is larger, that means you are more random. You have more choices. And when you have more choices, you are more random. I always give this example to my students. Let us say you enter a class and you see one student. What is the choice that you have? You only have one choice. So you are not at all random. So you have to pick that only one student and ask him or her the question. But let us say you enter the class and you see 60 students sitting in front of you. You are random. You have a choice. You can randomly select a student, pick a student, and question him or her. So the more the number of students you have, the more is the randomness, or in this case, randomness is directly connected to entropy. The higher is the entropy. So randomness is directly connected to entropy. Now the question, the original question, why do systems move in a particular direction? And the answer was the entropy of that system increases in a particular direction. Entropy of the universe or an isolated system cannot decrease. That in a sense means that nature prefers higher disorder. That is, nature prefers to move in a direction where the entropy increases. And I see this can be explained mathematically, but you can understand it intuitively that we always prefer a situation when we have more number of choices. Say, for example, again, I give an example. Say you go out for shopping and you enter a mall, and if there is the collection, we do not prefer a particular shopping mall when the collection is low. We say that no, I am not satisfied with this because they do not have the collection. That is, you are not given the proper number of choices. So it is a natural tendency for nature to always seek for higher number of choices. Just a second. Is the screen visible?
Yes, sir.
So it is the, so we always seek a configuration in which we have more number of choices. So we always prefer randomness. So always remember this is very intuitive. You probably can think of it intuitively that randomness is natural in the universe. Order is always forced. So whenever you are left alone, the natural tendency of a system is that the system will seek disorder, higher disorder. Order is always forced from outside. You can always force order, but disorder is natural. So a system, if it is kept or if it is left alone, the system is going to move towards higher randomness. So entropy of the system is going to increase. In other words, this number of ways in which you can have or achieve the same configuration is going to increase. Fine. But that still doesn't answer the question, why do we observe things happening in one direction? Now, the point is, that I'm trying to make, let me put it another way. You see, which configuration below has a lower randomness? If I ask you this question, you can see a pack of cards. The one to the left, you can see it has been arranged in ascending order. And the one to the right has been shuffled up. So my question is, which configuration below has a lower randomness? I know all of your answer would be the left one, because it is arranged in ascending order, it is in ordered state. And the one that is the picture to the right is shuffled, and you would say that it is highly random. But my question is, why? Why do you say that the figure to the right has a higher randomness than the figure to the left? Because, see, the question is very, very important, and that is key to understanding what I'm trying to explain. The point is, a configuration that is to the left figure and the right figure, both are a particular configuration, that is a particular arrangement of cards. So if you look at the left one and if you look at the right one, both are a particular configuration or an arrangement of cards. So why do we say that the left one is more ordered than the right one? The right figure is one of the many possible permutations that you can have with your cards. So it is a particular way of arranging the cards. You would say it is random, but that is my question. Why is it random? This to the right figure is a particular arrangement of cards. If you can see, this is a particular arrangement, a unique arrangement of cards. And to the left one, that is also a unique arrangement of cards. So why do we say that the left one is an ordered state and the right one is a disordered state? Think of it. We have never thought about it. And that is the key to understanding this concept. The answer came from Claude Shannon, who is called the father of information science. And I hope this is visible. So he was the first one who connected entropy with information. What he said, if you look at the figure, if you look at this, why? The question is why the left-hand side, the left-hand figure is more ordered and why the right-hand figure is not ordered or disordered. You see what Claude Shannon said? Claude Shannon said that in order to know the configuration of the system, you have to ask questions. For the right-hand side, you have to ask too many questions to know the state or the configuration of the system. But if you're clever enough, you can know the state of the system to the left by asking just one question. And that question would be, are the cards arranged in ascending order? And the answer would be either a yes or a no. So either a 1 or a 0. You see the concept of bits. Why? Again, see, I'm connecting entropy to information, and this is what information is all about. Claude Shannon quantified information. He was an American mathematician working in Bell Laboratories, and he's called the father of information science. He quantified information. Before him or prior to Claude Shannon, information was something very abstract. But this time, Claude Shannon, this fellow Claude Shannon, he connected information to entropy. And you can see the connection over here. If you want to know the configuration of this right-hand system, the right-hand picture, you will have to ask too many questions about, let us say, about the first card. You can ask, is it the king of hearts? The answer would be no. Is it a 4 of spades? No. And it would be random. So in order to know the configuration of this whole system, which is unique in itself, which is unique in itself, but you have to ask too many yes, no questions. But for the left-hand figure, again, it's a unique distribution of cards, but if you are clever enough, only one question will be sufficient enough to know the configuration of the system, and that question will be, are the cards arranged in ascending order? And the answer will be yes. So you know the configuration of the system. So what have you achieved? You have achieved or you have gathered information about the system. So the information content in the left system is less because you have to ask less number of questions. Whereas for the right figure, you'll have to ask too many questions. That is, the information content for the right hand figure is too high. And we know that the entropy of the right hand figure is also too high. So this was the relation that Claude Shannon made between randomness, that is entropy, and the minimum number of yes-no questions that are needed to be asked. And yes-no, the answer would be either a yes. If you denote yes by a 1 and no by a 0, again, it would be a string of bits. So he quantified information, and I'm not going into the derivation. This is not important. What he showed was the information content in the configuration of the system I is given by summation over pi minus of the summation over pi log to the base 2 pi, where pi are the probabilities associated with the random variable that is there in the configuration. I'll explain with examples. In some books, you would find this I as h, but I have written it I so that we can understand this is the information content in the system. So you can see there is a direct connection between entropy and information content. Entropy and information are directly the same thing, or they are related. Now, to understand with an example, let us say you toss a coin. What are the possibilities? The possibilities are heads and tails, right? And now let us say you toss a coin and Alice wants to send the outcome of that experiment to Bob. So either it will be a 0 or it will be a 1. So let us denote a yes by 1 and a no by 0. And what is the minimum number of questions that you can ask or you should ask? See, there is a word minimum. So you'll have to be clever enough to ask the questions. So what is the minimum number of yes, no questions that you can ask about the outcome of the experiment? The question is it a head? You could have asked, is it a tail? But in any case, the number of questions would have been 1. So is it a head? It's either a yes or a no. So that means you would send either a 1 or a 0. So you will be sending 1 bit of information. So this is the randomness of the system. You see, when you are flipping the coin, it's a random system. It can either be a 0 or it can be a 1. And the number of bits that are required to send the outcome of the experiment is also 1. And if you put it in the Claude Shannon's formula for I, you can see here that I is summation of pi. Now pi for head, the probability is half, and for tail, the probability is half. If you put in these values, log 2 of 0.5 into 0.5, you can see I have simply applied this formula and you will get a 1. So what is the information content? The information content is 1. That is the number of bits required to obtain the information about this tossing of a coin is 1. 1 bit is sufficient enough. Now, I'll move on to another example. Let us say you have a set of words and you pick a set of letters. You pick a letter at a random. You pick a letter at a random and you want to send that letter to your friend Bob. So Alice wants to send the letter she picked to Bob. So again, a yes is a 1 and a no is a 0. Let us say Alice picked up S. How many yes-no questions are required to send this outcome to Bob? So how many questions does Bob need to ask to Alice to know what letter she has picked? There are 26 letters. According to Claude Shannon, Each letter has a probability. You can see pi. Each letter has a probability of 1 by 26. So if you put in these values to the base 2, so you can see pi, the first one, pi into log 2 of pi, and you add them all. It was a summation and there is a minus sign. You would say it is 4.7. So around 4 and 5 bits are required to know the outcome of Alice. Now let us understand this. I said this is a minimum number of yes-no questions. How can you be clever enough to know? You will divide your data set into two parts. Now I can say, is it greater than m? The first one. The answer would be either a yes or a no. So in this case, if it is f, it would be a no. Definitely, so that means it is less than m. So I know. So that is a no. Next question is again, I divide the remaining data set into half. So I ask, is it less than G? Here you can find out G. Is it less than G? Again, the answer would be either a yes or a no. And this time, is it less than G? It would be a yes. Fine. Now, again, the remaining data set is divided into half. Is it greater than D? The answer would be yes. And finally, if it is greater than D and less than G, there are two letters remaining, E and F. So you can ask, is it E? The answer is a no. So how many bits have you sent? 4. But this is a specific example. So if you average for all possibilities and for all letters, the average number of bits that are required would be around 4, or between 4 and 5. So sometimes it would be 5 questions that you need to ask in order to know what is the outcome or what is the choice of Alice, or sometimes it would be 4. So on an average, it could be 4.7. So that is the answer. You can see it is matching. So that is the relation between entropy and information. Information and entropy are basically the same thing. So now let us go back and try to answer the questions that we were trying to find. Right. This. So what happens? You see, the marble is over here. Let's say you hold the marble over here. What are the questions? What is the question that you can ask about the energy of the system? Where is the energy? And the answer would be the energy is stored as the potential energy of the marble. Only one question. One way to distribute energy, right? But now if you release the ball or the marble, the ball will settle at the bottom. This potential energy is going to get converted to kinetic energy, and then finally with friction, this is going to be dissipated as heat, right? Now, if you want to know the configuration of the whole universe, what are the number of questions that you need to ask in order to know the configuration of the system? Where has the energy gone? The energy is gone out as heat. That is, it is taken away. When this marble slides down, it transfers its potential energy, kinetic energy to as heat. That is, it transfers it as the vibration of the glass molecules. The glass molecules vibrate and they transfer their energy to the air molecules, which again transfer their energy subsequently, and they are highly distributed. So the energy that was stored as potential energy, just one question, where is the energy stored? And the answer would be a 1. It is stored as the potential energy, it's gone. Now, how many questions do you need to ask in order to know the configuration of the system? Too many. And we do not have the answer. You drop a pebble in the pond. Where was the energy stored? It was stored as the potential energy of the stone. The moment it drops, it transfers its energy to water. Water, the ripples hits the shores and they transfer their energy to land. And finally, it is dissipated as heat. The molecules of land or sand or whatever there is vibrate and then they transfer it to air. So how many questions do you need to ask in order to know where is the energy distributed or where is the energy? When you started off, you had to ask only one question, where is the energy? And the energy was as the potential energy of the pebble. But now the energy is distributed. So how many questions? Too many, too many. What about the egg? The same case. Potential energy in the egg, it splatters, the yolk takes up, the yolk particles takes the energies, it distributes to the floor particles vibrate, the floor particles vibrations are transferred to the air molecules take it off. And they again redistribute among themselves. So how many questions? Millions and millions and millions and millions of questions. So why are these processes, or why do these processes happen in one direction? Because the information content is lost. What do we mean when we say that the entropy is increasing? We mean that the number of questions now we have to ask has substantially increased, and we cannot know practically the answers to those questions. So if we cannot know the answers to those questions, we do not know the configuration of the universe. And if we do not know the configuration of the universe, we cannot make the processes reversible. So that is why these processes are irreversible. Because, in other words, you can say there are two ways to answer that question. As a physicist, I would answer that why they are not seen in the reverse direction, because the entropy has increased. As a physicist, this is the answer. But as an engineer or as a computer engineer, why don't we see those processes happening in reverse? Because we have lost information. We have to ask too many questions, too many yes-no questions, and we will have no answers to those too many yes-no questions. So we do not know the configuration of the system. We had the information when we started, but now we do not have the information because it is too many bits of information, and we have lost it. So the information is lost. So whenever things are irreversible, it means that the information content is lost. So with this idea, I move on to the concept of classical computation. I'll just give you one scenario. This is done. Are classical gates reversible? Let's think about it. Here is the AND gate. And you have two inputs to the AND gate, and you know it's a one output. So here are the two inputs. Now, without doing anything further, can you tell me whether this gate, the AND gate or the OR gate or the NAND gate, which are the classical gates that do operations in classical computers, are they reversible? Look at the truth table. The truth table says you will have 3 zeros and you will have 1 1. So logically think about it. If you know the input, you definitely know the output. So if you know if it is 0 0 for the AND gate, the output is going to be 0. If you know it is a 1 0, you know the output is again going to be a 0. If you know the input is 1 1, you know that the output is going to be 1. But is the reverse true? If you know the output, do you know the input? I say if the let's say the output is 0. Do you know the input? No, because for 3 outputs, there are 3 different inputs. Same output, there are 3 different inputs. So logically, it is not reversible. And whenever some operation is not reversible, there is loss of information. Now let us see this mathematically. What is the information in the input content? You see 0 and 1, if you see the truth table, 0 and 1 occurs as a 50-50 chance. So it is a 0.5 log 2 of 0.5 again, and a 0.5 into log 2 of 0.5, which is 1. So the information content in the input is 1. If you want to have the information content for both the inputs, you multiply it by 2, you will get a 2. Fine. So you have 2 bits, A and B. You have 2 bits. Now what about the output? You see the output, there are 3 zeros. So the probability Pi for a 0 is 0.75 and the probability for getting a 1 is 0.25. And if I plug in into the equation given by Shannon, you would see that it is coming out to be 0.811. What has happened to the information content? The information content has decreased. That means the randomness of this AND gate has decreased. Information content has, why has the randomness decreased? You can understand it See, the input was very much random, 50-50 chances of 0 and 1. But if you see the output, 0 has a greater probability than 1. So the predictability of the output has increased. So if the predictability has increased, the unpredictability has decreased. So the randomness has decreased. And that is what is shown in the I out. That is 0.811. But we know that for the whole isolated system, that is for the whole universe, randomness cannot decrease. Or the information, see, this is the randomness. So the randomness has decreased. So if the randomness has decreased in the AND gate, where has the information gone? So what is the decrease in the information? The decrease in information is 0.811 minus 1. And that is minus of 0.189. So this is the loss of information that we have. So that means this information is lost. In other words, this has gone out. We cannot retrieve it back. So it is irreversible. Now let us see another example. What happens when we delete bits? We delete our memory, we delete our bits. What happens? Let's say there is a register and we have this combination. We have this combination 1001101, let us say, and we delete it or we reset it to all zeros. So what is the change in information or change in entropy of the system? So what is I in? If you see, there are 4 ones. So it is 4 by 7. There are 7 bits. So you multiply it by 7 and you get a 6.86 using the Shannon's formula. 4 by 7 and 3 by 7. 6.86. And what about this? What about this? What is the probability? 0 has only one probability of 1. So it is log 2 of 1 and that is 0. So there is no information in this. There is no information content in this. So what is the change in the information content? Or change in the entropy? The entropy has decreased for the system, not for the isolated system, not for the universe. If the entropy has decreased for the system, then somewhere the entropy must have increased. And that is not retrievable. I cannot get it back. So the information content is lost. And you can see very well, there was some information in this register which is being lost. And where is that information gone? And I have, in my previous slides, I've tried to convince you that information and entropy are one and the same thing. So if information is lost, entropy is lost. And if entropy is lost, it is lost as heat. So where is the lost information? It is lost as heat. So if the temperature of the surrounding is T, K is the Boltzmann constant, this is the amount of heat that is getting lost. Now please understand, this amount of heat loss is just due to the irreversibility of the classical gates. This is not, see, whenever, if our computers are running with power, with the help of power, so, and there are wires. So there is Joule heating in the wires, and we always have loss of energy because of the Joule heating of the wires. But I'm not talking about that. Even if you use superconducting wires with zero resistance, there won't be any Joule heating in that case. But if you are using classical gates, you would be giving out heat or you would be losing out energy. This is just because of the irreversibility in the classical gates. So classical gates are irreversible. And that is why, because of that irreversibility, we are losing information. We are losing heat. And a time would come that when, see, we are packing more and more transistors. We are packing more and more transistors in ICs. A time would come, there would be a huge, and they are getting faster and faster. So per unit time, they are performing more and more operations. And with every operation, they are losing heat due to irreversibility. They are emitting or they are releasing heat due to irreversibility, not due to Joule heating. I am not talking about the Joule heating of the wires. Keep it aside. Just due to the irreversibility, the logical irreversibility, they are losing information or they are releasing heat. And if you are packing more and more units or components in a single IC, and if they are running faster and faster per unit time, the computer is releasing more and more heat due to irreversibility. So what is the solution? The solution is quantum circuits, or quantum computing. Let us move on to qubit, the concept of qubit and quantum gates. So let us see if it solves the problem or not. So if you say, see, the analog of a bit in classical computing is called a quantum bit, and a quantum bit is called a qubit in short. And what is, I would suppose that you have the basic idea of quantum mechanics. Even if you don't, then I'll repeat. See, the basic idea behind quantum mechanics is the basic principle, or the basic thing that differentiates between classical and quantum is, just a second, something. Okay. So in quantum mechanics, if you take a superposition, see, in quantum mechanics, states can be in a superposition with each other. So you can have a 0 bit. This is a Ket notation. This is a Dirac notation. I'll try to explain this to you. This is a Dirac notation. This is for the 0 bit and this is for the 1 bit, let us say. I'll explain everything with time, but let's see what is the basic difference between quantum mechanics and classical mechanics. Is in classical mechanics you can have either a 0 or a 1, but in quantum mechanics you can have a linear superposition of a 0 and 1. So a qubit is in both 0 and 1. It's in both. It's a superposition of both a 0 and 1. This is weird. This sounds weird. Those who are not familiar with this property of quantum mechanics, but those who are, you know it, that in quantum mechanics, particles can exist in superposition states. So it's in both. That's the strangeness, that is the weirdness of quantum mechanics. So even a quantum bit or a qubit can exist in both states, that is a 0 and a 1. And that superposition, sometimes it is a special case. I'll come to this. It's a special case, which is written as this. What is general case? The general case is some coefficient A with a 0 vector. This is a vector. Please understand, this ket is a vector. This is called a ket. Plus B, which is a coefficient, which is a ket 1. So this is the 1 state and this is the 0 state. So the psi in general, this is the state of the bit, is in general a superposition of the two states, that is 0 as well as 1. And in general, you can write it as cos theta by 2 0 plus I e to the power of I phi sin theta by 2 1. Don't get intimidated by these formulas. I'll try to explain as much as possible. I'll come to this. For the time being, please note this formula. In general, this is the formula for psi. Now, please note this. This is a diagram. A classical bit is either in a 0 or in a 1. But a quantum bit can be in both, a superposition, and that's what makes all the difference. A quantum bit is in both 0 and 1. And here we are using, this is a diagram of a spherical polar coordinates, please understand. So if this is your axis, then this radial distance is referred as r. The angle that it makes with the z-axis is theta, and this, what it makes with the x-axis is phi. I'll come to this. Now this is a single qubit. Now what about 2 qubits? If you have 2 qubits, then the general state is given by this ket vector 0 0, 0 1, 1 0, and 1 1 divided by 2. I'll come to this. So in general, it is this with all these coefficients. Now let me tell you something very, very important. I'll write it over here. So please note that modulus of a square over here is the probability of finding the qubit in state 0. And modulus of b square is the probability of finding the qubit in state 1. And if you add the two probabilities, you must always get a 1. So please remember this. So mod of a square is the probability of finding the particle or the qubit in state 0, and mod of b square is the probability of finding the qubit in state 1. Whereas in physics, let us say, in physics, how will you implement the 0 and 1? It can be implemented as, for a spin of a particle, you know the spin of an electron can be spin up and it can be spin down. This can be referred to as a 0 state or a 0 bit, and this can be referred to as, the spin down can be referred to as 1. Or let me write it here. Just a second. So this would be a 1. Now you will know that the spin of a particle can be in a superposition of a 0 and 1. So it can be in a superposition of 0 and 1. So that is what I have written over here. So in matrix notation, what I have written down here is the 0 vector that is spin up, let us say. In matrix notation, you can write it in matrix notation as 0 and 1, and the spin down state, that is the 1 qubit, the part of the qubit that is 1, you can write it as 0, 1. So 0 and 1, a qubit can be in a linear superposition of these two. So let me go and try to explain this. You will need a bit of linear algebra knowledge. You will need linear algebra. So let me stretch upon this. You will need linear algebra if you want to understand this fully. But for the time being, I'll try to make you understand. So let us say, how do you denote a vector? So let us say that how do you denote a vector? So if I consider only two dimensions, let us say this is my E1 unit vector, and if this is my E2 unit vector, and this is, if you want to name the coordinates, then this coordinate is 1, 0, and this coordinate is, let us say, 0, 1, right? So how will you write it in quantum mechanics? I'll write in quantum mechanics this as a column matrix, 1, 0, this vector, this vector. I'll write it as 1, 0. And what about this vector? I'll write it as a 0, 1. That is what I'm trying to say. So a vector is denoted by a ket, in this case, in quantum mechanics, which is this. And this vector is denoted by another ket, that is 1. So this is state 1, and this is state 0. In physics terms, it is spin up, let us say, and this is spin down. So this is what you have. Now, what if I say that a linear combination exists? So if I go back to this, so if you say this linear combination, and if I ask you about this, the linear combination, So let us say you have 2 qubits. One qubit is in a linear combination like this, A0 with coefficient plus B1. So what is the probability of finding the qubit in 0? It is mod of A square. And what is the probability of finding the qubit in one state? It is mod of B square. So this I'll denote it by, let us say, qubit 1 state. And I can have another qubit, say side 2. It is again in a linear combination. Let us say C0 plus B1. So what is the probability of finding the qubit 2 in 0? It is mod of C square. And what is the probability of finding the qubit 2 in 1? It is mod of D square. What if I take the 2 qubits? In quantum mechanics, it is called the outer product, and that is written as this. And how will you do it? You will just take simple mathematics. You will just take this and this. So what do you have is, you have, if you expand this, this is the combination of the 2 qubits that I'm writing. You have this AC 0, 0 plus AD 0, 1 plus BC 1, 0 and plus BD 1, 1. Or see, I have just a second. I think I've gone ahead of my notations. So it's a 0, a 1, a 1, a 0. Now again, I can do a shorthand and write AC 0, 0 plus AD 0, 1 plus BC 1, 0 plus BD. So this is the combination of 2 qubits. You see this, a particular single qubit can exist in a superposition of a 0 bit and a 1 bit. So it's in both. If you take 2 qubits, what are the possible combinations of the two bits in classical computing? It can have 0, 0, it can have a 0, 1, 1, 0 and a 1, 1. Right? This is classical, but it can take only one of the 4 possible combinations at a time. But a quantum qubit, 2 quantum qubits, or quantum bits, sorry, can take all these possible 4 combinations at once. You see, this state is a linear superposition of all the 4 possible states that it can take. So that is, you can see, that is the difference. A single qubit, a single classical bit could either be a 0 or a 1. But I am saying a quantum bit, that is a qubit, can be both 0 and 1 simultaneously with different probabilities, A and B, mod of A square and mod of B square. Now, if I have 2 qubits, in a classical case, the two bits, classical bits, can have any one of these 4 values at a particular instant of time, but not all the 4. But a quantum bit, 2 quantum bits, can have all these 4 possible combinations at once. What about 3 bits? If you have 3 bits, you can have any of the possible 8 combinations in a classical computer. But in a quantum computer, or if you have 3 quantum bits, if you have 3 qubits, all the 8 possible combinations will exist simultaneously. And that is the power of quantum mechanics over here. And I repeat, so this is one that you have. So what is the, now if I ask you, what is the probability that if you measure this state is in a combination of all the four. So if you measure this state, what is the probability of getting a 0, 0? The answer is mod of AC square. That is the probability of getting a 0, 0 outcome. What is the probability of getting a 1, 0? It would be a BC mod square. That is the. And this is the notation. This and this, they are equivalently, they are same. So this and this, they are same. You can write it this way, you can write it this way. Sure. So this is how you write qubits. For a single qubit, you can write it like this, and for multiple qubits, you can do this tensor multiplication. This is called a tensor multiplication or an outer product. So you can do this. And you can have all the possible combinations. So if you have n bits, a classical computer or a classical register can store only one of the possible combination of 2 to the power of n. So there are 2 to the power of n combinations. A classical register can store only one at a time, but a quantum register can store all the possible 2n combinations at a time. All the 2n possible combinations. And I repeat, because this is very, very important. And I repeat, my 0 vector, I call it a state vector. Whenever I denote it by a ket, this is called a ket. You can see one line and this bracket. This is called a state vector. This in quantum mechanics is denoted by a 1, 0. And a 1 vector is denoted by a 0, 1. And this is called a block sphere that I had shown you. The north pole is the 0 state. And the south pole is the 1 state. So you can see this. This is what we have. Now, let's move on. I've already shown this. So what is the number of qubits required for a 1 GB RAM? 1 GB RAM. How many qubits? Work it out. 10 to the power of 9 bits. In classical, you need. But how many qubits do you require for that combination? Now, let's move on to, please work it out. Let's move on to Hadamard and CNOT gates. These are the 2 basic gates that we will be needing in quantum computing. So let us look at these gates. What are the Hadamard and CNOT gates? Hadamard gate is called the H gate, and this is a 1 qubit gate. It acts on 1 qubit, and this is the matrix representation. This is the matrix representation of the Hadamard gate. Again, I'll try to explain what this is doing, but let us see first that gate. So what does a Hadamard gate do? If you input a 0 to the Hadamard gate creates a superposition of 0 and 1. Can you see this? So you input 0, Hadamard gate is the one which creates a superposition. This is a classical one. So you see this, the input is a classical one. It's in state 0. But the output, you can see it's a superposition of 0 and 1. So whenever you want to create superpositions, you'll have to use a Hadamard gate. If you apply Hadamard gate to state 1, it gives out this. Again, a superposition, but the only difference is the phase of this 1 vector is reversed. You can see there is a minus. I'll show it. Then there is a NOT gate, simple classical NOT also. Even in your classical computers, the NOT gates are reversible. Even in classical computers, the NOT gates are reversible because it is one input, one output. The NOT gates are reversible. If you know the input, you know the output, and if you know the output, you know the input. So this is the quantum mechanical version of a NOT gate. You can see this is the matrix representation of NOT gate. What it does is, if you apply NOT gate to 0 state, it gives you 1. And if you apply NOT gate to 1, it gives you a 0. Correct? And that is the matrix representation. I'll come to the matrix representation. Try to explain why this is such a matrix. A 2-qubit gate is a C0 gate. This is one of the most important gates that you will encounter. And the matrix representation is this. Again, how do we denote C0 gate? Again, it's a 2-qubit gate. Now, C0 gate needs 2 qubits. Like the Hadamard gate needs 1, the NOT gate needs 1, the C0 gate needs 2 qubits. Let us say it needs A and B. And what it does is, it's a NOT gate, but a controlled NOT. So C0 stands for controlled NOT. So it controls the NOT operation. So here you can see the truth table. By this truth table, you can understand if the input, see this X is called the control bit. So I write it over here. X is called the control bit. And Y is called the target bit. Y is called the target. Right? Now, what do you have? You have a 0, 0 input. The control NOT, what it does is, if the control bit is 1, then it flips the target bit. I repeat, if the control bit is 1, it flips the target bit, and if the control bit is 0, it does nothing to the target bit. So you see here this one, right? So it is basically 0, 0. The control is 0, the target is 0, it does nothing. The output is 0, 0. The control is 0, the target is 1, it does nothing. 0, 1. The control is 1, the target is 0, it flips the target. The control is 1 and the target is 1. Again, it flips the target, that is, it makes it a 1, 0. So you see that this is the truth table for a controlled NOT. And if you look at the target bit, just the target bit, so I've written it over here. C0 on a 0, 0 is 0, 0. C0 on a 0, 1 is 0, 1. C0 on a 1, 0 is 1, 1. C0 on a 1, 1 is 1, 0. It flips the target. Now, if you look at the last part, if you look at the last part, the last part is 0, 1, 1, 0. It's nothing but an XOR operation. It's the output of the XOR. It's the output of the XOR gate. The XOR is an exclusive OR. You all know this. You all are familiar. When either of the two inputs are 1, only then it gives an output 1. Otherwise, it is a 0. So you see the target bit is an XOR, and that is why you have a symbol over here. Look at the symbol. A is the control bit over here. A is the control bit, and B is the target bit. So whenever A is 0, it does nothing to B. But whenever A is 1, it flips the bit. And this is nothing but A XOR B, the symbol that is written over here, and A is retained. I think somebody was asking me in the chat box, what about the XOR gate? The XOR gate is it reversible? No, it is not. Logically, it is not. The simple classical XOR gate is not reversible because I told you there are 2 bits that you require for the input. And for the output, if you put the Shannon's formula, that is 0.5 log 2 of 0.5 plus 0.5 log 2 of 0.5, the output is 1. So there is a loss of information. But look at this. there is an additional output also. You look at the XOR table. I think this is this. I'll come back to this. So the question is, are they reversible? Let me answer that question. Are these gates reversible? That is what we are trying to do. The Hadamard gates, the CNOT gates, these are quantum gates. Are these gates reversible? So let us try to understand that question. But before that, there was a question in the chat box. And if you look at the classical XOR operation, you have A input, you have B input. 0, 0, 0, 1, 1, 0, 1, 1. And if you have the A XOR B, then you have a 0, 1, 1, 0. This is what. So what is the number of, what is the information in the input? It is 2. The information is, this is not working. The information is 2, the information content. And what about the output? What about the output? What about the output?
Tanmoy sir,
Huh.
another question is there, how the matrix is derived.
I'm coming.
Okay.
I'm
Okay.
coming. But my pen is not working right now, so I'm a bit stuck with it.
Okay.
So
Please take your
please
time.
bear with me. I am stuck with this. I'm stopping the share so that I can again share it. Was this light or was this? Anything else? So right. So let us see if I. Okay. So I output, if you ask me, what is I output? I output is 1. See, 0.5 probability for a 0 and 0.5 probability for a 1 output. This is 1. Now, if I ask you what, if you know the input, do you know the output? Yes. For a classical XOR, you know the input, you know the output. But if you know the output, do you know the input? No. And that is what is shown mathematically over here also, that the information content decreases. Technical glitches. Right, so this is what you have. But in a quantum CNOT gate, you see, if I draw the truth table, A, B, A remains the same. And in case of B, it is A XOR B. So it is 0, 0, 0, 1, 0, 1, 0, 1, 1. So what do you have? You have a 0, 0, 1, 1. That is same, but here you have a 0, 1, 1, 0. Now this, please understand, in C0, this is the output. And again, the information content is 2. Because for this, it is 1. And for this, it is also 1. One question. For this, it is 1. For this, it is 1. So the change in I is 0. That is, the change in entropy is 0. That means it's a reversible process. And I'll show you these are reversible. I'll show you by other methods also that these gates are reversible gates. Now, let me move on to the matrix representation of the gates so that you understand. Now, before moving on to this, I'll do a bit of linear algebra. I have always emphasized this, and I'll keep on emphasizing this, that if you want to learn quantum computing, you have to go through linear algebra and vector spaces. That's the very, very important. That's the prerequisite for understanding quantum computation. So I'll do a bit of it. Now let us say again, I have a coordinate axis. This is E1 and this is my E2. Fine. So how do I represent my, in this case, I'll not do it by this. I'll just write it as E1 and E2. So E1, if I write in matrix notation, I'll write it as a 0, 1 component. And E2, I'll write it as a 1, 0, 1, 1, 0 and a 0, 1. Now, if I ask you, what is a matrix? In mathematics, you have done this matrix and all, but let us understand this matrix in a more physical perspective, which is necessary for quantum computers. Now, what is a matrix? Let us say I have a matrix. I have a matrix, let's say 2, 1, 3, 4. This is a matrix. You can easily say, okay, if I ask you that this matrix is M, what happens if I operate this matrix on E1? You get some other vector. Let us say you get a vector A. Let us. So what does it do? You see that if I operate this matrix 2, 3, 1, 4, that is this equation, if I do on E1, what do I get? I get a 2 and I get a 3. Am I right? I think correctly. Now, where is 2, 3? If you see, I told you this is the coordinate 1, 0. This is the vector. This is the vector, which I have represented it like this. And this is 0, 1. I have represented it like this. Now, where is 2, 3? Now, if I extend this, where is 2, 3? This is 2, and this probably would be 3. Let us say this point. I'm not getting this. So let us say this is 2, 3. So what is this vector? This is another vector. This is A. This is A. This is the vector 2, 3. So what has this matrix done? This matrix has physically rotated E1 to this place, and it has also stretched E1. So matrix is nothing in physics but an operator. It's an operator. So in quantum mechanics, we denote operators by matrices. Operators mean you are operating something. Operating something on what? You will be operating something on the state vector side. Whatever is the state of the qubit. It can be in a superposed state, or it can be in a single bit state, either a 0 or 1, or it can be in a superposed state. So whenever you are operating an operator means mathematically an operator is a matrix. And what does a matrix do? You have seen, if you look at this diagram, if you look at this visualization, then the matrix is something which takes a vector and it rotates the vector, or it stretches or squeezes the vector. Right? Now, you have heard of this eigenvalue equation. Let us say I tell you M, and if you multiply it with a vector X, you get lambda X. This is an eigenvalue equation. You have done it. Let us understand this physically. What does it mean? What are these? You know, that means X is an eigenvector. X is an eigenvector of M, and lambda is the eigenvalue. You have done this in mathematics, but what does it mean physically? So say, for example, this is my vector. Now I'll rub this, and what I'll do is, again, let me take the vector as E1 itself. Let me take the vector as E1 itself. Now the matrix M is, let us say, 2, 0, 0, 2. This is my matrix. And if I say, if it operates on E1, what is the result? So 2, 0, 0, 2, it operates on 1, 0, same vector that I've taken previously, and it gives me a 2 and a 0. And if I take the 2 out, it gives me a 0, 1. That means M of E1 gives me 2 E1, which means that now E1 is an eigenvector of the matrix M with an eigenvalue of 2. What does it mean? That when, see, in the previous case, when M operated on E1 with a different matrix, it rotated the vector and stretched the vector. But if it is an eigenvector of that operator, that matrix, then it will not rotate the vector. The span remains the same in mathematical terms. It only stretches the vector by a 2, you can see. So if this is the eigenvector of this matrix, so what it does is, it does not rotate the vector, but it stretches the vector by an amount of 2. And the amount of stretching or squeezing that is happening is nothing but the eigenvalue. So understand, matrix is something, matrix is, in quantum mechanics, matrix is represented by an operator, and a state vector are matrix operators are represented by matrices, and a state vector are also represented by column matrices, and operators are represented by square matrices. And understand, when there is an operator operating on a vector psi, it changes the state of the vector generally. So whenever you have an operator which operates on psi, the vector state is generally going to change to some new vector. Like this one. It operated on E1 and it changed the vector to something, some another vector, let us say. But if it is an eigenvector, it does not change the span of the vector, but it squeezes or stretches it. So this is the general way to write the equation. Now coming to the gates. How are these gates represented as matrices? Now gates, what do gates do? In classical computers, gates are the operations on bits that we do, AND gate, OR gate, XOR gate, or whatever. The gates do this. Similarly, in quantum computing, the gates are the operators. So gates are something which is doing something, the operation, they are doing something on the qubits. So how do you represent gates mathematically? You are going to represent gates mathematically by operators, right? So the Hadamard gate, I told you that is the Hadamard gate. The Hadamard gate is given as 1 over root 2. This is the matrix of Hadamard gate. This is the matrix of Hadamard. And if I tell you, if I apply Hadamard gate on 0, what do I get? What is my state 0? My state 0 is 1, 0. And what is my state 1? My state 1 is 0, 1. So if I apply Hadamard gate on 0, what do I get? I have a 1 by root 2, 1, 1, 1 minus 1, and I apply it on a 1, 0. So I have a 1 over root 2, I have a 1, and I have a 1. How can I represent this? A 1, 1 can be represented by a 1, 0 plus a 0, 1. That is, it can be represented as, this vector is nothing but the 0 state. This is nothing but. Now, I told you that any state vector can be generally, if you look at the slides, it is generally represented as, I told you, I told you I'll be discussing this, cos theta 2 plus e to the power of I phi sine theta 2, theta by 2. This is 0 and this is 1. Now, what does the Hadamard gate do? In this case, this is the general representation of state. Now, the Hadamard gate on 0 gives me this combination. So, the Hadamard gate on 0 gives me this combination. So, if you look at this combination, then cos theta by 2 is 1 over root 2.
QRC sir, please unmute yourself.
I was mute the whole time.
No, not for a few seconds.
Oh. So was I audible for this matrix operation, the Hadamard operation?
Yes, you are.
Okay, so what I was trying to tell is, so if you operate Hadamard on this, you'll get a 0. So if you compare it with this, you see sine theta by 2 is also a 1 by root 2. So a theta by 2, so what is this? So a theta by 2 is nothing but, in this case, if you find out, it is a 45 degree. So what is theta? Theta is nothing but 90 degree in this case. So the Hadamard gate, what it does is, it rotates the 0 vector by 90 degrees. This is what the matrix operation of Hadamard gate is. It rotates the vector by 90 degrees around, let us say this. So I think I do not have space over here. So let me rub this. Please understand this. So if you look at that block sphere representation I had shown you, the north pole was, this was your x-axis, this is my y-axis, and this is my z-axis. This is state 0, right at the north pole. This is state 1, right at the south. If I apply a Hadamard gate to this state, now the vector is here, spin up, let us say. I apply this gate will rotate it to this side. See, theta is 90 degree for a Hadamard gate when you get this. So that means after applying the Hadamard gate, the qubit is now going to be oriented along positive x-axis. This is what. So it is nothing but a rotation. It is nothing but a rotation. What is the NOT gate? Look at this. What is the NOT gate? The NOT gate is 0, 1, 1, 0. That is, if you apply NOT gate, so I can rub this all. I'll start with again. So the NOT gate is 0, 1, 1, 0. And you fly. This is also called the sigma x gate. This is, if you study quantum mechanics, I'm not going into the detail. This is also called the Pauli matrices. Pauli's matrices. So this is called a sigma x, or simply put x. This is called also x. So that is represented as this. So if you apply an x gate on 0, what do you have? You have 0, 1, 1, 0 on 1, 0. You just have a 0, 1, and that is nothing but a 1. So a NOT gate on a 0 gives you this. Similarly, a NOT on a 1 would give you a 0. So what does a NOT gate do? Block sphere, this is 0, this is 1. So a NOT gate, so if this is my bit in 0 state, it flips the bit by 180 degrees. So it rotates this. So this is a matrix that represents rotation by 180 degrees. Hadamard gate is a rotation by 90 degrees, and it places it along the x-axis. So this state, the Hadamard gate does is it places the bit along this axis. So this is a superposition of 0 and 1. You can see. I again repeat, this is the, after the Hadamard operation, it is along the x-axis. Before, now this is 0 and this is 1. So you can see the Hadamard gate, this now qubit is a superposition of a 0 and a 1. So you half the times if you measure, you will find 0, and half the times if you measure, you will find 1. So the state that is represented by 1 over root 2, 0 and 1. I told you if you measure this qubit, you will find mod of a square. The probability of finding a 0 is mod of a square, and that is 1 by 2, 50%. And the probability of finding a 1 vector is mod of b square, that is again a 1 by 2. That is 50%. So that is what Hadamard gate does. And that is what a NOT gate does. Now the question was, were these gates reversible? Now I ask you a question. Let us convince ourselves, because that is very much required. Let us convince ourselves that, first of all, let me write down the Hadamard gate again. That is 1 over root 2, 1, 1, 1, minus 1. I know that the Hadamard gate on a 0 will give me square root of 2, 0, minus 1. Oh, sorry, plus 1. Now, what about a Hadamard on a 1? So do it. That's why I told you I want you all with pen and paper. That is the Hadamard gate on a 1. And that is equal to 1 over root 2, 1 and a minus 1. How can I write it? I can write it as a 1 over root 2, 1, 0, minus 0, 1. So that is equal to 1 over root 2, 0 vector minus a 1. Is it okay? So a Hadamard gate on 1 is, you'll have to keep this in mind because I'm going to need this later on. This is what you have. The Hadamard. So it rotates the 0 vector by 90 degree, also the 1 vector by 90 degree. Now I wanted to tell you that are these gates reversible? Now you apply Hadamard gate on these states again. What do you get? What do you get? So I ask you, if I apply, now you have this state. So you have this state, 1 over root 2, 0 plus 1. I say that you apply the Hadamard gate on this state now. Again, 2 Hadamard gates. What do you have? So it's a linear operator, the Hadamard gate. It would operate on a 0 and then it would operate on 1. Is it okay? So what do I get? I get a square root of 2. This another square root of 2 should be there. Because now the Hadamard gate is again operating. So another square root of 2, 0 plus a 1, plus another square root of 2, 0 minus a 1. And if you add it, 1 over 2 is common. If you add it, you would get a 2. And that is nothing but again a 0. You see, you have retrieved the initial state. So you have a 0. Please understand. You apply Hadamard gate. What do you get? You get a 1 over root 2, 0 plus 1. You apply another Hadamard gate to this input. You get back. So it is reversible. So applying 2 Hadamard gates means doing nothing over here. Similarly, Hadamard gate on 1 over square root of 2, 0 minus 1 will give you 1. So convince yourself about this. I won't be doing this. I have done this for you. Hadamard gate on this will give you 0 back. And Hadamard gate on this will give you 1 back. So Hadamard gate is reversible. Similarly, C0 gate, it is reversible. C0 gate is reversible. How can you prove that? How can you prove that? I am rubbing this off. And how can we prove that? Let us say we have 2 states and we have all the 4 combinations. So what do we have? We have all the 4 combinations, that is 1 by root 2. Let us take this state. 1 by root 2, another qubit. So what is the combined qubit state? It is psi A, psi B. What is the combined qubit state? The combined is 1 over 2. You have a 0, 0. I told you this before. 0, 1, 1, 0, plus 1, 1. This is what you have. Now, if you apply a C0, see, if you apply a C0 to this state, C0 to this state, what do you get? C0 to this state. So you have, I'm doing it in a separate line, you have a half. Please understand, we can do it very quickly. This is the first qubit. This is the second qubit. If the first qubit is 0, it does nothing to the second qubit. Again, if the first qubit is 0, it does nothing to the second qubit. Right? If the first qubit is 0, or if the first qubit is 1, it does not, it flips the second qubit. And again, if the first qubit is 1, it flips the second qubit. So after applying C0 on this, you get this. Now, if you again apply a C0, what do you get? Half, 0, 0, 0, 1, 1, 0, plus flips it. You get back this. So again, C0 is again, they are all reversible gates. They are all reversible gates. And there is another gate that I wanted to show you, and that is called the controlled not. And then maybe I'll move on to the hands-on a bit, because you might be bored with all these mathematics. So we will do some hands-on. But before that, I'll discuss one more gate that is important. That is called the controlled not. There are 2 controls. It is also called a CC not gate, or the other name is the Toffoli gate. What it does is, draw the truth table for you. It's a 3 qubit gate. Now, it's a 3 qubit gate. So A, B, C, these are the 2 control bits. Now there are 2 controls, and this is the target bit. So again, there will be A, B, and C. That is, or not C, but something else. So the combination 0, 0, 0, 0, 0, 1, 0, 1, 1, or 0, 1, 0, 0, 1, 1, let us say, this 0, 1, 0, 8 are there. So what does the control not do? It takes 2 control bits. Only when the 2 controls are 1, it flips the target. So here it is same. Same, nothing, it does. Because only when the 2 are 1, it flips. 1, 0, 0, 1, 0, 1. Now see the last two cases. 1, 1, there are two controls are 1, it flips it to 1, the target. 1, 1, it flips it to 0. Now this would be very, very important. This case, this truth table. Now if I take, just separate from the table, if I take only for the inputs for C, the target, if I only choose the target to be 0, not 1, then what does my truth table look like? So this is the one that I'll select. This is the one that I'll select. The target is 0. The target is 0 initially. And this one, the target is 0. So if you separate out these 4, what do you get? I'll just write down the A, B, C and the output. This one I'll write. So it is 0, 0, 0, and the output is a 0. Then it is 0, 1, 0, the output is a 0. Then it is 1, 0, 0, the output is again a 0. And then it is 1, 1, 0, the output is a 1. I'll forget this because everything is set to 0. What is this truth table? This is an AND gate. A classical AND gate, which can be done using the quantum circuit. I'll show you. So these are the two inputs. And this is the output. So I have to set my target bit to 0. I cannot set my target bit to 1. And if I set my target bit to 0, my Toffoli gate will work as an AND gate. So let us do some hands-on so that I can show you something. Let us do some hands-on. You'll have to have an account at IBM Quantum Experience. Is my screen visible?
Yes, it is.
So here you have, see, you have to create an account with IBM, and they will give you the access to their quantum lab and quantum composer. And here you can play with circuits. You can build your own quantum circuits and you can submit them. You can run them on simulators and you can run them on actual quantum computers, which I'll show you today. Now I'll launch the composer. You see, I am launching the composer. Just taking a bit of time. No, yeah. Is this screen visible?
Yes, it is. And you may ask the participants also to do it in real time.
So participants, if you have logged in or if you have created an account with IBM, you can do it in real time. So here you can see these are the qubits. Q0, Q1, Q2, these are the qubits. And initially all the qubits are initialized to 0. Here, this white means it is 0. You can see the probability of 1 is 0. You can see it is written over here. The probability of 1 is 0. So it is a 0 bit. So it is initialized to 0, all the 3 bits. So what I want is, I just want to show the Hadamard one. I just wanted to show the Hadamard one. Now here you can see these are the gates. Now what if I apply a NOT gate? You can see this is a NOT gate. So what if I do, if I apply a NOT gate? You can see this. It changes to a complete blue, which is a 1. And this is the state vector diagram that is drawn below. Let me drag it. Yeah, you can see this is the probability of getting 1 is 100. So I can do it in probabilities. The probability is 100%. What if I remove this? You see the probability of getting a 0 is 0. So it flips the gate, flips the bit. Now let's see if I apply a Hadamard gate. to 0. You know what a Hadamard gate does. It creates a superposition. That is, there will be 50-50 chances. Now you can see this. 50% is white and 50% of this is blue. 50% of this is blue, and here is the diagram, the computational state basis. You can see 50% of the time it is 0, it will give you, and 50% of the time it will give you 1. Now let me show it to you on a real quantum computer. This is a simulation. Please understand, the simulation will always going to show you the ideal case, 50-50 chance. But let us run. You can see there is a top right hand corner, set up and run. So what I do is I click here, and here there are many quantum simulators and quantum computers online, and there are jobs you can see that is there. So I will run it on IBM QSCM simulator, and I can choose the number of shots. Let us say I choose the number of shots to be 100. 100 times I want to measure that state, that superposed state of 0 and 1, and I run it. It may take some time. Okay, it needs a measure. Okay, fine. So what I do is right. Now I set up and run. Now I set up and run. No need to bother about this. This is a measurement case, so I have to measure it. This is what a measurement. So you see there's a new job result over here. It has been run on an actual quantum computer. Just see, 100 shots, 100 shots. You see this. How many times have I got a 0? 47. And how many times have I got this? 53. You see, on an actual quantum computer, if you run it 100 times, you won't get exact 50-50. But if you increase the number of times, the possibility of getting that exact 50-50 will be close. You see, the number of times you get a 0 is 47. The number of times you get a 1 is 53. What I do is, I again do the same thing, but this time with 2000 shots. Or I reduce it. Let us say I reduce it to 25 shots. Let's see what happens. Or not 25, I should have made it 26. In any case, I can see it. You see this? You see this? This is truly random. The number of times you get a 0 is 15, and the number of times you get this is 10. You see, you do not get a 50-50 part. You only get a 50-50 part when you run it many times. It would approach a 50-50. When I ask you what is the probability of getting a heads, you say it is 50%. But can you guarantee that if you toss it twice, you will get once a head? No. That 50-50 probability is if you toss a large number of times, then out of that, half of the times you would get a heads and half of the times you would get a tails. Now, what I do is I increase the number of shots. I increase the number of shots to 2000. Let us. And I run it again on an actual quantum computer. So let me wait for a bit. There is a new job result. Right. Look at this. 2000, 1029 outcome. 10 frequency out of 2000, 1029 it is giving a 1, and 971 it is giving me a 0. So it is coming to 50-50. Ideally, this will always give you a 50-50. If I remove this, this will always give you a 50-50. So you can see here that whether your things are correct or not, if your circuit is correct or not. So you can see this. So you can, sorry. So you can see this 50-50 chance. Ideally it is this is 50-50. You can see this. Ideally it is 50-50, but when you run it on an actual quantum computer, you see the results are. Right, I think 2 participants have raised their hands. Can you unmute them?
Yes, just doing it. Sanjay Sardar.
Yeah, Sanjay
Yeah,
Sardar.
yes, you can unmute yourself. It's Sanjay Sardar and Gaurav Banerjee. Both of you, you can
Hello.
unmute yourself. Yes, Gaurav, please.
Good morning, ma'am. Good morning, sir. Actually, I was telling that my this one is not completing, means it's still pending. The time you it took for you and the time it's taking for me, I think I don't know what's the reason, but still pending. The result is still pending. I tried doing this.
What quantum simulator have you used? There are many quantum simulators. You see, if I have you put the measurement one?
Yes, yes, sir. The thing you did say, I did the same.
Okay. So there is a setup and run. You go there. There are many simulators. You can see a simulator state
Okay,
vector.
okay, yes, yes,
So
yes,
you
yes.
see the last one, IBM QASM simulator. You run it on that. I generally do it there, but I can use the simulator state vector also. You can see how many devices are online over there and how many qubits it is there, the simulator. It is 100, 5000 series. These are the qubits. And you can select your number of shots. You can select your number of shots to run it on an ideal quantum computer. And all of you, please note that here is a code also to the right. So if you want to write it in Qiskit, this is another open source by IBM, and it runs on Python. So if you people know Python, then this code is written in Python. So you can copy that code and you can go in Qiskit, and that this is called the Open Quantum Lab, and you can write your code in Qiskit in Python, and you can run it there also on quantum computers and quantum simulators. They are available online. You can build your own circuit. Understand this. You can build your own circuit and you can submit it. Let's say you're developing some apps for a company or anything, some games. You can build a quantum circuit and you can send it. So this is a brilliant interface to work on. And you can see this is what happens. Now I remove this.
Tanmoy sir, Tanmoy
Yes.
sir, Preeti Pranima Rodriguez. I think she wants to say something. Ma'am,
Yes,
please,
yes.
you can unmute yourself. No, I think no more. Sanjay Shorter, sir.
Sanjay sir, is it okay now? You run it. Probably there is a server error, but you can always do it.
Okay.
Okay, so let me move on with this now. Fine. So let us work. I showed you the AND gate. I showed you the AND gate. Let me do it. Let me do it. So let us create an AND gate over here. Let us create an AND gate. And if you remember that it is basically a Toffoli gate with the inputs. So I remove this. I remove this. You see, these are my two inputs, X and Y, Q0 and Q1. If you remember the AND gate, I told you the AND gate is nothing but a Toffoli gate. When the last qubit, the C qubit, it was set to 0. So Q2 is initialized to 0. I know this. So I just need a Toffoli gate. What I do is I just drag in the Toffoli gate. You see, this is a controlled not. One control is at Q0, one control is at Q1, and Q2 is knotted depending on the two control bits. So this is a CC NOT gate that I've dragged and dropped. Now look at the inputs. You see, what I do is I put a barrier. I can put a barrier over here so as to denote my parts of the circuit. Let me edit the gate. Yes. Right. So another thing that I put is here. Let me edit the gate. Yeah. So that is the barrier. Now that is a CC NOT gate. Now you see, it's an AND gate. It's a simple AND gate that you can see. So it's Q0 is 0, Q1 is 0. These are the two inputs. Q2 is the output. You can see it is 0. So 0, 0, it is a 0. I want to check a 0, 1. How can I make Q1, 1? I'll have to drag in a NOT gate. So that is a NOT gate. Now look at the outputs. The inputs are these. It is 0 because it is complete white. Now this is 1, complete blue, and look at the output. It is a 0. So 0, 1, it is a 0. I want a 1, 0. So I put the NOT gate here for the first. So you can see this is a 1, complete blue. This is a 0, Q1, second input, and this is a 0. So 1, 0 is a 0. I want a 1, 1 input. And let us see what is the AND gate.
Tanmoy sir, there is another one.
All AND
Ganesh.
gates. Yes.
Ganesh sir, he wishes to ask, I guess, something. Sir, you can unmute yourself.
Yes, Ganesh sir.
Sir, namaste.
Namaste sir.
Sir, myself Ganesh from Odisha. मैं पहली बार इस प्रोग्राम में ज्वाइन किया हूँ, तो मुझे क्वेश्चन कुछ नहीं डिक्लेयर करना है, बस मैं इसे जानना चाहता हूँ, और मैं होल सेशन में ध्यान से आपका प्रेजेंटेशन देख रहा हूँ, तो आई थिंक मेरे मन में ऐसा कुछ नहीं है, तो मैं कंसिस्टेंसी में देख रहा हूँ, और आप जो बोल रहे हैं मैं सुन रहा हूँ, बस इतना ही सर।
Okay, thank you sir. Thank you.
Okay, welcome sir.
Thank you. Something somewhere. Shourjo, can we look at C0 or CC0? Can we look at C0 or CC0? I'm not getting. Shourjo. No, in AND gate it's a CC0. In AND gates it's a CC0. It's a 3-qubit gate. You want at least 2 inputs and this output. CC0 is a 2-qubit gate. CC0 is a 3-qubit gate. So this is what. Is it okay? So I think there are many things that I want to share till now. So this is an AND gate. You see a 1, 1, and the output is 1. The output is 1. So I'll come back to this. But I have many more things to do, and I have the algorithm to discuss. So coming to that algorithm, I'll try to answer the questions if I want to finish the presentation. The algorithm is a Deutsch. It's called the Deutsch algorithm. It is probably the first quantum algorithm that will show you the power of quantum computing. Now, till now, what we were dealing with, I think we answered the questions that quantum gates are reversible gates. And that is what was the main problem with classical computing. I told you classical gates are irreversible. And that is why there is an information loss. In other words, there is heat loss. But quantum gates, I showed you, they are reversible gates. And in reversible gates, you have no information loss, and that's why you have no heat loss. So you can check on that. But there is yet another power. This is not the whole story. There is yet another power of quantum computers, and that power will be demonstrated by this algorithm. This was the first quantum algorithm given by David Deutsch, and it's called the Deutsch-Zosa algorithm. Now look at the problem. The problem is, I think you all should be with me, and I hope you all will do this work with me. Be ready with your pen and paper, and we do it. Now, let us say there is a binary function. A binary function, let us say it is fx. What is a binary function? A binary function is it takes binary inputs and it also outputs binary values. So it can output a 0 or a 1. So there are 4 possibilities for this binary function. What is the question? The question is the binary function fx, is it a constant or a balanced? Let us understand what is a constant function. See, the arguments can be f0 and it can be f1. It is constant when f0 is equal to f1. That is, it does not depend on the inputs. Whatever is the input, the value is same. It outputs, the function outputs the same value. f0 is equal to f1. And balanced means F0 is equals to F bar 1, F not 1. That is whatever is F0, F1 is the opposite of that. So if F0 is 0, F1 is 1. Or if F0 is 1, F1 is 0. So it means it is a balanced. So the question is, how do we determine whether Fx is constant or balanced? See, in a classical algorithm, in this case, for one bit, you have to check at least twice. Fx, you have to check at least twice. But in a quantum algorithm, you'll have to evaluate Fx only once. I told you right from the beginning, I have tried to make things as simple as possible. The mathematical rigor of this derivation is, it's quite mathematically rigorous. But I've tried to make things very simple for you. We could have generalized to n bits, but I'm trying to do it with 1 bit only. So let us say, look at this table. So my input can be 0 and 1. And these A, B, C are my fx's, outputs. What can be the output? If it is 0, F0 is 0, F1 is also 0. So irrespective of the input, the output is 0. So this is a constant function, the first column, A. This is a constant. Now, what can be the second one? Whatever is the input, it just brings out that input. So 0 to 0, 1 to 1. So you can see half of the time you get a 0 and half of the time you get a 1. So it is a balanced function. Or what it can do is, it can invert the function. So again, you get a 1 for a 0 and 0 for a 1. So half of the time you get a 1 and half of the time you get a 0. So again, it's a balanced function. Or you can get one value, fx value. These are the fx values for both the inputs. So again, this is a constant. So the first and the last are constants, and the middle two, in between the two, they are balanced functions. So how many times do you have to check fx? So it's a function, whatever it does. I am not interested what is the mechanism of that function. What I'm interested is what is the output of that function, what it does. So I want to know, the question is fx constant or is fx balanced? Right? So what do I need to do? I have to check. In classically, I have to check it twice. At least I have to check it twice. That is for a 0 and 1, I'll have to check f0. Let's say f0 gives 0. Will that tell you that f is a balanced function or a constant function? No, because f0 can be 0 in both the cases. If it is constant, then f0 can be 0. Or if it is a balance, f0 can be 0. So next what you have to do is you have to check f1. If f1 is 0, then it is a constant function. If it is 1, then it is a balanced function. So how many times classically you have to check this function? You'll have to check this classically twice. And quantum mechanically, you'll have to evaluate fx once. Let's see how. And then I'll try to generalize this to n qubits and see the power of quantum computing. So what is the algorithm? The algorithm is, you have two inputs, x and y. You have this. You have a C0 gate. You all know from now that what a C0 does. It outputs this x as it is, and it knots it with y. You see, it knots it with y, XORs it with y. Sorry, it XORs it with y, C0. So whatever is the x, it XORs it with y. Now, what about this algorithm? This is a black box. What I want to tell you, this is a black box. I don't know how it functions, but I know that it contains that f function. It evaluates fx, whatever is x. And I want the fx to be XORed with y, this input. The output is x, and this output, the second output, is changed. It is XORed with y. It is XORed with y. So this function basically evaluates. So what it does, it evaluates fx, and then it XORs it with y. Right? This is the quantum circuit. Now, what can I do? How can I do it? Evaluate once. You see, let us say my input is a 1, not a superposition, but a 1. And another input is also a 1. Let us. And here is the function. Here is the function inside this black box. Here is the function. So I put this one through a Hadamard gate and I put this one through a Hadamard gate. What does the Hadamard gate do? It creates a superposition. So here you will have a 1 by root 2, 0 minus 1. And here you will also have a 1 by root 2, 0 minus 1. Correct? So it enters this black box. So what it does is, it does this output. Now this output, remember this output, this one, it computes fx and it XORs with the second input over here, y, whatever, this is y. Now this is my x, this is my x, and this is my y. The superposed states are my x and y, the one that are entering the black box. So this black box evaluates that function and XORs it with y. Now, I apply a Hadamard gate. This is the circuit. I applied the Hadamard gate to the first output and I do nothing. That is, this is the identity operator. I do nothing to the second output. Let's see how it works. Let's see how it works. So if this is my circuit, now I have divided my circuit into 4 parts. This is part A, this is part B. The barriers that I was drawing in my quantum lab, B, C, D. So what I do is, let us find out the wave function at every point. Psi A. The wave function is, it is simply 1 and 1. So 1, 1 and 1, 2. So this one, the subscript, these refers to the bits, the first bit. So this is the first bit and this is the second bit. And this one is the state. This one is the state, this state. So it passes through the Hadamard, this passes through the Hadamard. So what about psi B? Psi B over here, you can see. So as I told you, this will be a linear superposition, this will be a linear superposition. Now if you have this tensor product, and I told you how to do it, you expand psi B. You expand psi B, you get a 1 by 2 out, you get a 0, 1, 0, 2 minus 0, 1, 1, 2 here, minus 1, 1, 0, 2 plus a 1, 1, 1, 2. Correct? Now what it does? It evaluates fx. I repeat, it evaluates fx. What is x? X is the first qubit that is entering. Y is the second qubit that is entering. In every combination, the first qubit is x and the second qubit is y. So what does this black box do? This black box takes the function fx and it XORs it with y and outputs that XOR in the second output, leaves the first output unchanged. You see, this is x itself here. And what about this? This is fx XOR y. Okay, this one, this part. Now what is psi b? Now what is psi c? Here, psi b is written, fine. I have expanded it. Now what you do is you keep the first bit. See, please keep the first bit same, 0 same, 0 same, 1 same, 1 same, because it does not change the first bit, first qubit. So 0, you can see 0, 1, first pay attention, 0, 1 over here, 1, 1 and 1, 1 over here. But what about the second one here? Here, what about the second one? What it does? It takes the fx and it XORs it with y. Now, please understand, if you XOR something with, let us say, I'll just erase this. You have fx. Fx can take 0 or 1 value. If you XOR fx with another 0 or a 1, so if you XOR fx with 0, what will you get? You will get fx itself. You know this. Because if fx is 0, 0 XOR 0 is 0. And 1 XOR 0 is 1. So if fx XORs with 0, you get fx back. And if fx XORs with 1, you get fx bar. That is the complement of fx. You see this? If fx is 0, then you XOR with 1, you get a 1. That is the bar of fx. You have fx 1, you XOR with 1, and you get a 0 bar of x. So keep this in mind. Keep this in mind. These two things. You XOR fx with 0, you get fx back. You XOR fx with 1, you get a complement of fx. Now what about this? Look at this. It first computes fx. Fx is f0 because the first is 0. Look at the first one. The first is 0. So f of 0, and it XORs with the second one. The second one is 0. Here. So it takes the f of 0 and XORs with 0. So you have a f0 in the second bit. Look at the second part. F of 0, because x is 0, you have an f of 0, and you XOR it with 1. Because y is 1, the second qubit. So you have a complement of f0. Whatever f0 is, I do not know what f0 is. Whatever f0 is, the complement of f0. The third one, you have 1. 1 remains unchanged because the first qubit is same, 1. But you take f of 1 because the function of the first qubit, and you XOR it with 0. So you have an f of 1. The last one, 1 remains unchanged because the first qubit. Now you take f of 1, the function of this, and you XOR it with this. So you get f of 1 complement. Am I clear? I hope I am. So you have all of this. So I will erase this. This is what. This is psi c. This is psi c. Now, can I factor things out? Can I factor things out? Now, if f0 is equals to f1, please understand this. If f0 is equals to f1, that is, if it is constant. If it is a constant function, then you see this f0 and f1, they are the same. So I can factor it out. So you see, I factor f0 this. So I factor this out. So please, I just write this 0, 1 minus 1, 1, and I have factored out f0, 2. I factored out because f1 and f0 is same. So I factored it. This is what I have. And if f0 is f1, then f complement 0 and f complement 1 are also the same. So I can also factor them out. So what do I have for the second one? I have a minus of half. I can write 0, 1 minus a 1, 1, and I can factor out f02 complement. You see, f02 complement is the same as f1 complement because they are, let us say they are constant. So what you have this common. You have this common. So here I have written, you see this is common. You see this is common. And you are left with f0 minus f complement 0. Now I have factored it out. And what can I write about this? So, and if they are, okay, fine. So I can write it like this. And if they are not balanced, if they are not constant, if they are balanced, what do I mean when I say they are balanced? That means f complement of 0 is equal to f of 1. That they are balanced. And if that is true, then f complement of 0 and f of 1, they are same. These two are now same. So I can factor this out. These two are both the same. These two are the same. So I can factor this out. So if I factor this out, and F02 and F complement 1, they are the same. If I factor this out, I'll get this. I am not bothered about the second one. You see, this is the second qubit, second output. I have factored it out. See, there are two outputs, this and this. This is the first one. This is the first output. And first output. This is the second one. I'm not bothered about the second. I'm bothered about the first. So what can I write? What can I write? I can write this as square root of 2, 0 minus 1 into square root of 2 F0 2 minus F complement 0 2. The first one. I'm writing just the first one. This one. This one. So I have this as my first qubit. You see this. Let me go back to this. You see this. This. So if I factor it out, so what I have is the output at psi c. If I factor it out, I'll have a root 2. See the first case, 0, first qubit. And a 1 by root 2. F of 0 minus F complement of 0. I have factored it out. Here also I have factored it out. Here the first factor would be root 2 plus 1. And there is a factor. Now remember the circuit. This is psi c. Please remember the circuit. Just a second. This was psi c. This is psi c. Now you have to apply a Hadamard on the first qubit. So if it is constant, look at this. If it is a constant function, the first qubit at C is this. And if it is balanced, the first qubit is this. And if I apply Hadamard on this qubit, you realize if you apply Hadamard, you will get 1 as the output. And look at this. If you apply Hadamard on this, you will get 0 as the output. So in one shot, so if for fx constant or for a constant fx, the Hadamard operation on the first qubit, this qubit, gives 1. And if fx is 0, balanced, then Hadamard operation on the first qubit gives you 0. So in one shot, you know, just by looking at the output of the Deutsch algorithm, just a second. Just by looking at the output of the Deutsch algorithm, what I want to tell you is, if you get a 1 in this output, fx, whatever this fx is, this is constant. And if you get a 0 over here, you know that fx is balanced. You do not have to check it twice. You can check it through this circuit only once, and you will find that whether fx is constant or balanced. Let me just illustrate this point. So let us say, just imagine this. Let us say there are 2 qubits. Now, instead of 1, there are 2. What are the combinations? The combinations are 0, 0, 0, 1, 1, 0, 1, 1. Let us say. And the output is 0, 1, 1, 0. Let us say this is fx. So what do I mean? I mean that f00 is 0. You take the 2 inputs. Previously, it was f0, 1 input, and it was giving an output, either a 0 or a 1. Now F01, it's a 1. F10, it's a 1. And F11, it's a 0. Let me ask you a question. In general, if there are n bits, how many times, to be on the safer side, how many times can you try to check out whether fx is balanced or constant? Here in this example, fx is balanced, you can see. Because half the times it is giving me 0 and half the times it is giving me 1. It is a balanced function. So how many times do you need to check? Let us say you are lucky enough and you check F00 and F01 randomly, and you get 0, 1, and you immediately know it is a balanced function. But if you are not lucky enough, you might check F00 and you might check F11. You will get a 0, 0. You are not sure whether it is balanced or constant. You are getting a 0, 0, but the other two might be 1, 1, or it might be 0, 0. So what you have to do, you have to check one more, at least F01 or F10. If that is different from 0, then it is a balanced function. And if that is equal to 0, that is a constant function for 4 possibilities. So how many, for n bits, how many possibilities are there? How many combinations can you have? You can have 2 to the power of n combinations. Like this, you can have 4 combinations. How many times should you check? At least 2 to the power of 2 to the power of n divided by 2 plus 1. That is what I'm trying to say. So if there are 2 bits, so you'll have to check it at least 3 times. Because you might be lucky to check 2 times and find out. But classically, to be sure, on the safer side, you have to check it on an average 3 times. So this is the formula for n bits. Imagine if there are 100 bits, what is the average number of times you have to check whether fx is balanced or constant? You have to do it 2 to the power of 99 times plus 1. This many number of checkings on a classical computer you have to do to find out whether fx is balanced or not. In a quantum computer, you can do it in one shot. Imagine the power. Parallel computer. Because where is the magic? The magic is over here. Let me go back. You see the magic is over here. When you are creating a linear superpositions by the Hadamard gates, all the states are present. And then this black box is computing F0 as well as it is computing F1. These are parallelly processing it, you can see, because the qubits that you have entered, they are in a linear superposition. This black box is going to check for fx. And remember, x is a linear superposition of all the possibilities. So f of all the possibilities will be checked simultaneously in one shot. Whereas in a classical computer, you will have to check for 2 to the power of 99 plus 1. And if each computation takes 10 to the power of minus 9 seconds, you can imagine the number of time it takes. It will be in some billion years to complete this checking process. So that is called the computational complexity of the problem. It reduces the time complexity. Please understand the power of quantum computing. All the Fs, it will compute simultaneously because the bits that are entering, they are basically in a superposed state. And the black box, what it is doing is, it is finding the value of fx. So simultaneously for all combinations of x, it will check for fx. And if you know that if you have a particular output, like in this case, you will just check the output. In this case, you will just check the output. If the output on the first qubit is 1, then fx is constant. And if the first qubit, if you measure the first qubit and you get a 0, you know that it is a balanced function. So let me go back a bit and let me tell you, do something very, very useful with you. We are almost there, I think. Let me do some hands-on things with you. Share screen. So let me do something. Let's see. Let's see. So you all know about the half adder circuit, the adder circuit. Let us construct an adder circuit in this IBM experience. So what I do is I'll delete this. Second. So what I do is so I'll take another one. Now I'll put take a C0, extend it here. Just bear with me and we will understand this. This. Now put a barrier. Here. To denote this is my adder. So this is my adder circuit. Now you know in an adder circuit there is a sum and a carry. So this is my sum Q2. Okay. So this is my Q2 is the sum and my Q3 is the carry. So what are my inputs? Q0 and Q1 are my inputs. Look at this. So I have a C0 operator from Q0 to Q2, the sum, the one that will carry the sum. Another C0 operator from Q1 to Q2, and a CC0. One control is at Q0 and one control is at Q1 and the other is at Q3. So if my input is 0, 0, you see Q0 and Q1, you see these are my sum and these are my, this is my carry. You see both are 0. Now what I do is, if my input is 1, 0, what is the sum? You see my input is 1, 0, my sum is 1 and my carry is 0. You can see. What if my input is 0, 1? You can see my input is, the first one is 0, the second one is 1. That is my input. And this is my sum. My sum is also 1. And my carry is 0. What if my input is 1, 1? 1, 1 input, you know that the sum is 0 and look at the carry. The carry is 1. So this is a half adder circuit. We have just constructed a half adder circuit using quantum gates, the C0 and the CC0 and the NOT gates. This is the half adder, the one within the barrier. Because if you remember the half adder circuit, please understand the sum was an XOR operation and the carry was an AND operation. You see, I have already told you this is the AND operation, the CC0. So this Q3 is the carry. You see, it is the AND operation. It takes the output, the AND operation. And what about the sum? It is basically the CC0 operations. So this is the sum. If you go through your half adder circuit, the classical half adder circuit, the sum is an XOR operation and the carry is an AND operation. So this is what you have for a half adder circuit. Right? Now, I tried to do the Deutsch algorithm. I tried to find the algorithm. See, I tried to find the algorithm online so that I could show it to you, but there was no such quantum circuit for Deutsch algorithm for 1 qubit. So I designed my own. I'll show you. This is, I have done it on my own to show you the Deutsch algorithm that we right now discussed. So let us see the Deutsch algorithm. So you remember the input was 1, 1. If you go back to the slides, the input was 1, 1. So what do? I put a NOT bit. You see, these two are 1, 1. So I put it over there. Now what I do is, I delete this bit. What I do is, you remember there were Hadamard gates for both. That was my second part of Deutsch. The input was 1. Both the ones were put through the Hadamard gate to create superposition. Now there was the oracle, that is called the oracle, which computes the fx and XORs it with y. Now, what can be a balanced circuit, or what can be a balanced function? The balanced, you can see the Hadamard gate itself outputs balanced functions because it outputs both 0 and 1. The Hadamard gate outputs both 0 and 1. So I have to do nothing. I can put an identity operator. That's my balanced oracle, fx. It does nothing. If it is 0, then it is basically this Hadamard outputs both. The output of this Hadamard is, the first Hadamard is, it outputs both. It is a linear combination of 0 and 1. So it is a balanced circuit. So I put a barrier to show the oracle, or to show the black box, let us say. Right. Now, you remember, I have to do a C0 with the second y. So Q1 is my y. So I do a C0. I do a C0. And then I put a barrier to show this is my whole black box. And then if you remember, in the first qubit, in the output, there was a Hadamard. What circuit is this? This is a balanced circuit. You see, both 0 and 1 are coming. Fx is both. What is this I doing? What is this I doing? This is computing the fx, identity operator. Whatever x is coming, x is, remember, it is a superposition of 0 and 1. Whatever x is coming, it is outputting that. So it is outputting both 0 and 1. So it is a balanced function. What is the output that you are getting? You are getting a 0 as an output. You remember, if it is a balanced function, it will give you, the first qubit will give you a 0, and it is giving you a 0. What about a constant function? See, if you are not sure, keep your hands on this, above this circuit, the barrier that I have drawn, this UF, the black box. You can keep your hands. You do not know, please understand, you do not know what is happening inside, how it is computing fx. All you know is the output of the first bit. The first bit is 0. You know that whatever this function is doing, this function is a balanced function. Now, what about a constant function? Let me add 2 more qubits. Now, I have created a constant function. What I do is I cut these two. Now, I have to make a constant function. What I do is I take a CC0. And what I do is I put it over here. That's a CC0. And then I knot it with this. You see? Let me edit this.
TRC sir, please remove that current file on the composer's job portion.
Okay. So this is my black box. I do not know what the black, this is, I have just made it for you to understand. This is a constant function. Please understand, this CC naught is doing something constant. See, why? Because the Hadamard gate out of Q naught, it is giving you a superposition of 0 and 1. So it is giving you both 0 and 1 as the output. Here, my cursor, it is giving you both 0 and 1. But you see Q3 is some bit, which is the target bit, and the control bits are Q2 and Q0. Q2 is always 0. So whatever is Q0, 0 or 1, since this is a CC naught gate, one control is with Q0 and the other control is with Q2, Q3 will have, nothing will happen to Q3 because Q2 is always 0. It will not invert Q3. Whatever is Q3 will be constant. So this output over here will be a constant because Q naught is a superposition of 1 and 0. This first one, this is a superposition of 1 and 0. But whatever is 1, whatever is it is, 0 or 1, it is not going to affect Q3 because Q3 is the target bit where the control bits are Q2 and Q0. But Q2 is always 0. So whatever you do with Q1, Q0, you cannot change the output of Q3. So this is a constant function. And then this output of this function is knotted with this second y. This is my y. C0. You can see the C0 operation. So this is my fx. This control naught is my fx in this case. And this is the C0. So this is a constant function. And what is the output? The output is 1. So for a constant function, the output is 1. And for a balanced function, the output is 0. So this is 1. And I could go on a bit, but I think I'll have to stop it. But I can just show you something which is very, very, I feel which is very, very relevant to the topic. Let me just because I won't take much time here, and I'll just what I'll do is, this is just to show you, please, to see the power of quantum mechanics, just to the quantum computing, just to show it to you. So what I'll do is, okay, this circuit is called the entangler detangler circuit. Let us say, do not get intimidated by the name again. Please understand, this first qubit is with Alice, let us say. And the second qubit, Q1, is with Bob. And these are entangled pairs. I am not going into the details. These are entangled pair. What I want to show you is something else. So this Q0 is with Alice and Q1 is with Bob. Now, what can Alice do to send 2 bits of information using one single qubit? Please understand. Alice has only one qubit, Q0. And Bob has one qubit, Q1. What can Alice do to send 2 bits of information using her one qubit that Alice has? What Alice does is she sends her qubit also out, and Bob has these 2 outputs, one for Alice and one for Bob. Fine, but let us say Alice wants to send 0, 0 to Bob, 2 bits of information to Bob. Alice does nothing to this circuit. What is the output? The output for Alice is 0 and the output for Bob is also 0. So Bob gets the Alice's qubit and Bob has his own qubit, that is 0, 0. So Bob knows Alice wants to send 0, 0. See, Alice has only one Q0. She has done nothing. Now, what if Alice wants to send a 0, 1 using her qubit? See this, see the magic. Alice puts a NOT gate to her qubit inside here. See, Alice is doing this. Alice does not have Bob's qubit. Alice is doing something to her qubit. She has only one qubit. And with this encoding, she has sent this to Bob. And now Bob has Alice's qubit and his qubit. Now see the two bits that Bob has, 0, 1. She has encoded the message 0, 1 in her qubit. Remember, she has only one qubit, her own qubit. And she does this to her qubit and she delivers it to Bob. And Bob has these two outputs. What if she wants to send a 1, 0? What can she do to her qubit? I'll remove this and I'll put this operator. This is called the Z operator. You see, she does something to her qubit and it encodes a message for both the qubits. And Bob gets a 1, 0 output. So Bob knows, okay, this is the message. But Alice has only one qubit. Now, what if Alice wants to send a 1, 1 message to Bob? What can she do to her only qubit? She does something to her qubit and she sends 1, 1 to Bob. So using a single qubit, she is sending a message for two bits. A 2 bits message is being sent using a single qubit. This is called super dense coding using entangled pairs. So if you go deep into quantum computing, you will know what is super dense coding. And in super dense coding, you will see that Alice does something with her qubit to convey. She has only one qubit and she conveys 2 bits of information to Bob. She does some manipulation to her qubit and Bob has information about 2 bits. So that is called super dense coding. So this is one that you have, and I've shown you half adder, I've shown you the AND gate, I've shown you the Deutsch algorithm. This is, you can play with the circuit, you can run with the circuit, you can run the circuit using an actual quantum computer and see the outcomes of the measurements. You can write your own code using Python. These are the codes you can see. These are written, or you can play with this quantum composer and you can run it from quantum simulators. I think we are finally here. So for the further study, I have discussed only one, that is Deutsch Zosa. You can go for Grover's search algorithm. It's a quantum search algorithm, reduces the time. Shor's algorithm is very, very important for factorization. And you know that nowadays cryptography, encryption is being made using RSA algorithm, and RSA algorithm is nothing but it is a prime factorization techniques. And the greater the number, the higher or the greater is the time taken by a classical computer to factorize. And that's why it is so secured. They cannot factorize within polynomial time. But if you have the Shor's algorithm in place, they can factor this in polynomial time. So you can break a code or you can break the password. So this is very, very, Shor's algorithm is very, very important as far as quantum cryptography is concerned. So in defense, you can use it if it is properly constructed to break enemy's codes. Then entanglement and quantum teleportation. As I told you, IBM has teleported a qubit. Please understand, it is not transportation, but it is teleportation. IBM has teleported a qubit. Without a physical transfer of a qubit, IBM has teleported a qubit from one place to the other. So it can be done using entanglement. Then I told you, I gave you an example of quantum dense coding. Quantum cryptography. If quantum cryptography comes into picture, no one will be able to hack. Because in quantum mechanics, there is a theorem, if you go into it, it's called the no cloning theorem. you cannot make a copy of a quantum state, identical copy of a quantum state. The moment you try to make a copy of it, you are destroying it. The wave function is collapsing. And that is how you are disturbing the state. So you cannot make a copy of a state. And if you cannot make a copy of a state, or if you are trying to eavesdrop, then you will be inherently disturbing the system. And in the process of disturbing the system, Bob and Alice, the legitimate parties, would know that somebody has disturbed the system. So quantum cryptography, again, very, very important. DRDO is spending lots of money in quantum cryptography. In recent years, I have heard that government of India is trying to spend 8,000 crore rupees in quantum computing. US is spending $1.2 billion to build quantum computers. And you want to have an idea of how physically quantum circuits are implemented. This is the Sycamore Google's 53 qubits quantum processor. This is the highest. So far, I think IBM has one also for 53 qubits. You can understand how fast it can operate. It has solved problems in 200 seconds, where the problem which a classical computer takes around 10,000 years. And this quantum processor has solved it in 200 seconds. And this is the link for IBM's quantum composer. I told you this link you can take. You can log into the IBM site and you can create an account, and they'll give you a passkey, and then you can start composing your circuits and play around with the circuits. Thank you. I am done. So now I can take questions if time permits.
Yes, sir, we have very little time. I think Nala Yak is there. She has a question.
Okay. Yeah. Yes, ma'am.
You can unmute yourself, ma'am. No, not getting any response. Sir, Dr. Jane Christie, ma'am is asking for some reference books on quantum computing for beginners. Her message is it is quite interesting to apply digital and quantum mechanics together. So if you suggest some books.
See, one book that I know is Nielsen and Chuang that you can study. It's a good book that you can study, but for beginners it is good. But I would suggest you go to the IBM site, and they have a PDF version of quantum computing. They have all the algorithms: the Simon's algorithm, the Grover's algorithm, the Shor's algorithm, the Deutsch algorithm, and all the quantum circuits that you need. And they'll show you how to apply. They'll show you how to write codes in IBM Quantum Composer or the Quantum Lab. There is it's a PDF version. It's available in the IBM's website. Please search for that quantum computing book by IBM. It's there. I have read it, and it's brilliant. The explanations are very, very good, very, very good. And Nelson and Chuang is one book that we can go through, and it's an emerging technology. People are all over writing. Internet is a rich source of learning, so always do that. But IBM's book the PDF book is very, very good. It's very, very good. Yes, I'll be happy to answer. Yes.
Ma'am, you can ask your question. Nala, yeah, I guess.
Shayon Day is here. Shayon Day has said how CC NOT gate is a reversible gate. I told you, if you see, if it is an AND gate. No. See, AND gate, you do not retain all the inputs. You just have the output. But if you look at the CC NOT gate, it's a 3-qubit gate. 3 inputs, 3 outputs. So you know from the outputs, you know what the input is. You look at the CC NOT gate, and I have shown you that if we apply CC NOT gate twice, you will get again this. You'll get back the same number. So please understand, CC NOT gate is a 3-qubit gate. There are 3 inputs, 3 outputs. So just by looking at the output, if just a second, can I share the screen for Shannon? Let me. Okay. Here, please. Let's see here. So let me do it on this only. Understand this. The AND gate, CC NOT gates works as an AND gate. It can mimic the operation of an AND gate. But remember, CC NOT gate is an AND gate only when the third input is 0. I told you I have removed the rest 4. So this is the AND gate. If you look at the truth table, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. So if you look at the input, you can know the output. But if you look at the output, you cannot know the input. But what about CC NOT gate? I have drawn the truth table for you. The output is unique. The output is unique. So it is 0, 0, A, B, C. Here you have A, B, and C XOR with AB. That is what CC NOT is, both. So it is 0, 0, 0, 1. Let's write down the input first. 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Now I'll keep these the same. So you see, this is the output. So this is the input, and these are the output. So this is all 3. This is the input, and all 3. This is the output. So it is a 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1. So here you have a 0, 0, 0, 0, 0, 0. And here you have a, what is here? It flips it. So you have a 1, and here you have a 0. This is what. Right? Look at this. So this is just a second. This is what? 0, 1, 0, 1, 0. This I think I have not done. This is what. Sorry about this. So this would be 1. This would be 1. Because C remains the same. C remains the same. And I think I've made. What about the 2 other? 1, 2, 3, 4, 7, 8. Look at the output. The output is there might be something else. I think 1, 0. Yes. Here. There it is. This is what. So you see, this is the output, and the outputs are unique. So from the output, if you look at the output, can you tell the input? Yes. If you have a 1, 1, 0, you know that the input was 1, 1, 1. If you have a 1, 1, 1 output, you know the input was 1, 1, 0. You see, the outputs are unique. It's a 1-to-1 mapping. But what about this? Are the outputs unique? No, they are not. Is it okay? So CC NOT, please understand, CC NOT is an AND gate when you only take C's 0, these 4. Only then it mimics an AND gate. Otherwise, no. So completely CC NOT gate is a reversible. It has a unique output for every input. I hope I have answered this. Anybody else?
Tanmoy sir, in chat box there is a question from sir. What are QISKIT and SARQ? Are they similar to Python? What is used?
Python is the programming language that you will use in Qiskit. Qiskit is something there you will have to write the code that I've shown you. And in Quantum Composer, you just drag and drop the gates and you can see the output, and then you can run it on a quantum simulator that I have shown you, the quantum simulator. You run it on an actual quantum computer and you find out the results. The same you can do using Qiskit. In Qiskit, you can write the code. You'll have to write the code, and the language that you are using for writing the code is Python. So you'll write the code in Python, and then you will execute that code again in a quantum simulator or an actual code, and then you'll get the histograms and all that. Okay. So the language used is Python. Yes. Anything else?
I guess no more questions are there.
Okay.
So I guess we are thank you Tanmoy sir for this insightful session.
Thank you.
I hope our participants, though it was quite a complex, but I hope our participants have received a glimpse and beauty of quantum computing. Now we are nearly at the end of today's session. Before wrapping up, on behalf of Basic Science Department, I wish to thank you all the participants for your participation and cooperation. Actually, we organized this webinar just in 1 week preparation, and it could not be possible without the active support from our chairman, sir, Mr. Kishan Kumar Kejriwal, principal, sir, Professor Abhijit Lahiri, and Dean Academics and Administration, Dr. Orgho Sarkar. I want to extend my sincere thanks to all of them. Thank you to all our seniors who motivated us to arrange such kind of webinars. A special thanks to Mr. Ajay Singh for his active cooperation through the entire time. So I guess just before wrapping up, just let me check if there, no, there is no more questions. So formally, we are ending up today's session. I wish to end up the session with a quote of Abraham Lincoln: determine the things can and shall be done, and then we shall find the way. So I hope quantum technologies surely will lead the way. Thank you all.
Thank you.
Thank you, sir.